So you should be memorizing your element names and symbols from the list. So that was back here. Okay, so make sure that you are doing that. However you like to memorize things. You need to be able to spell the names correctly, and you need to be able to write the symbols correctly. You may have noticed, if you've started doing this, you may have noticed that there are some symbols that don't seem to go with the names, and that's because those elements have been known about for a very long time, and they had originally had Latin names, and so the symbols come from their Latin names. So the Latin word for gold was aurum, and that's why its symbol is AU. All right, so pay attention to those. And today we're going to talk about properties of matter. And we're going to start off by talking about physical properties and physical changes. So a physical property is defined as a property that we can observe with our five senses, or with a tool that extends our five senses. So sight, smell, taste, touch, sound. Usually we don't use taste in the chemistry lab because that can be dangerous. And smell we use very cautiously, as well as touching substances. But things like microscopes really just extend our ability to look at something. Thermometers extend our ability to know how hot or cold something is. And so things like color, density, odor, those are all examples of physical properties. Physical changes are changes that occur to matter where the molecular makeup of the matter doesn't change. And usually this has to do with moving our particles either farther apart or closer together. So remember when I did the demonstrations for you last week, we said that when we heat matter, the particles move faster and they get farther apart. That causes a physical change. The molecules stay the same. They don't change. And so this can be a little bit confusing for students because anytime we have a change of phase or a change of state, that is a physical change. All that's happening is our particles are getting closer together or farther apart. So on this slide, there is a picture of a water molecule here. And we all know the formula for water is H2O. A chemical change would alter that. It would change it from H2O to something else, okay? A physical change for water, the molecules are going to stay H2O. So you can see in our pictures here, if we go from a solid to a liquid, and then from a liquid to a gas, our particles are still H2O. It's still water. All that's happening is that the particles are getting farther apart. And when we go this direction, go from a gas to a liquid and a liquid to a solid, same thing. Okay, our particles are just changing the distance that they are apart. So phase changes are always physical changes, all right? So in a chemical change, something new is produced. So remember we talked about how in a chemical reaction we have reactants that we start with, and we have products that we end up with. And the reactants have their own properties. The products have their own properties too, but they're different from what the properties of the reactants are. The other thing about chemical changes is that it has to do with breaking old bonds and making new bonds. Kind of like when we talked about that Lego set that you can take apart and put together in different ways. Unfortunately, we can't see the breaking and forming of bonds. Okay, so we have to rely on something else to tell us that a chemical change is occurring. And so the word macroscopic means big, sort of like microscopic means small. Macroscopic means big. So these are things that we can observe that tell us indirectly that atoms are breaking bonds and making new ones. Okay? So a change in potential energy, sort of like if you've ever used a cold pack. When you get the cold pack out, it feels normal. When you crack it, the temperature gets colder, right? That's a sign of chemical change. There has to be a chemical reaction to make that occur. So we can't actually see the bonds that are being broken and formed, but we can see the result of that, which is a change in temperature. Another thing that we can see is the production of a gas. We don't mean like if you shake up a bottle of pop and the gas comes out, because the gas was already there. You're not making any new gas. But if I have two solutions, and they're not fizzy in any way, and I mix them together, and all of a sudden now I have bubbles, or like if you've ever seen vinegar and baking soda, okay, that formation of a gas is a chemical change. That's a sign that there's a chemical change occurring, okay? Another example is a change in color. This is not like if I take red food coloring and I put it in a beaker of water and the water turns red, because the red was already in the food coloring. This is if I have two clear, colorless liquids and I mix them together and all of a sudden they're pink. Okay, that's a color change that shows that a chemical change is occurring. And then the fourth sign that we look for is the formation of a precipitate or a solid. And this is the same type of thing. If we have two clear solutions and we mix them together and a solid forms, or it gets cloudy, that's a sign of a chemical change. And we're going to see some of these things tomorrow. I'm going to do some demonstrations for you. So those are the four things we look for when we think about, when we're looking to trying to decide whether we've got a chemical change or not. And so the chemical properties of substance have to do with whether they can interact with other substances to make a chemical change. So when we mix baking soda and vinegar, we get bubbles, and so we know that that's a chemical change. Knowing that if I mix them together, they're going to produce bubbles, that would be a chemical property of baking soda and a chemical property of vinegar. Okay? So the property is the ability to interact with some other substance and have one of these changes occur. All right? Okay, so if you look in your notes, there's a little table there, and we have a color code. So the yellow stands for a physical change. You can either use the colors or you can just use the abbreviations. Physical change is PC, chemical change is CC, physical property is PP, and chemical property is CP. So if you would read through those examples and see if you can classify those. And I'll just give you a couple minutes. So here are the answers. So in the top left corner, when it says my eyes are brown, whenever we identify the color of something, that's a physical property of that substance. Ice melting is a phase change, so that's a physical change. When we have taken a measurement of something like the density or the mass or the length, those are physical properties. Paper burning is a chemical change, and the sign that we would see would be a color change. Our paper would be going from white or whatever color they are, usually to black, and we would probably see little particles breaking off, little black particles breaking off the soot. Dissolving sugar is actually a physical change. It doesn't alter the sugar molecules at all. Okay, so the sugar molecules stay intact, they're just not in a crystal structure anymore. Same thing as grinding chalk to dust. It's still the same compound. We haven't changed the compound. It's just in smaller pieces. At the top of the second column, the fact that litmus can change to blue or red is a chemical property of litmus. Okay, so litmus can change color depending on whether it's in an acid or a base. So that's a chemical property. Scratching a design into glass is a physical change. Vinegar has a strong odor, that's a physical property. Cutting your fingernails, a physical change. The fact that aluminum foil is shiny is a physical property. When we mix vinegar and baking soda and it creates a foam or a gas, that's a chemical change. At the top of the third column, the fact that hydrogen is explosive is a chemical property. That means that it can react with oxygen and cause an explosion. The next two, substances, the fact that a substance is brittle and the fact that sugar can dissolve in water are physical properties. The fact that zinc has the ability to react with hydrochloric acid is a chemical property. Evaporating alcohol is a physical change because remember the particles are just getting farther apart. We're not changing the alcohol particles. Again, here we have a measurement, the melting point of butter. That's a physical property. Fireworks exploding is a chemical change. Our floor tile is 30.45 centimeters across. That's a physical property. Wood is able to burn in air. That's a chemical property. Football has a mass of 410 grams. Physical property. Chopping lettuce, physical change. Copper wire can conduct electricity. That's a physical property. And I'll tell you that ones that most students kind of get tripped up on is this one, dissolving. Okay, it seems like it might be a chemical change, but it's not. It's actually a physical change. Evaporating, that's a physical change, right? And then this one, the fact that copper wire can conduct electricity. There's no chemical change in that. When we're conducting electricity, we're just forcing electrons to move through a wire, kind of like if you have water running through your garden hose. It's the same type of an idea. So there is no change in the substance when we conduct electricity. Adding food coloring to water, soda foaming when shaken, and water boiling, those are all physical changes. We kind of talked about those already. Apples turning brown in the air, there's obviously a color change. That's a chemical change. Sandpaper is rough and gritty, physical property. And a beaker falling and breaking is a physical change. Okay, so those three that I circled, those are the ones to kind of watch out for. Those are the ones that most students miss on a test or quiz, okay? So now that we know about properties, what we want to be able to do is we want to be able to categorize elements. And there's three big groups of elements: the metals, the nonmetals, and the metalloids, okay? And so we're going to talk about the characteristics of these groups, and we're going to also talk about where they are on the periodic table. You might remember from physical science or ninth grade science, that valence electrons are the electrons on the outermost ring of the atom. They're the ones that are involved in bonding. Metals tend to have very few valence electrons, 1 or 2 or 3. And those electrons are held very loosely, and so metals tend to lose their electrons, okay? And when they lose those electrons, they become a charged particle called an ion. And we call these ions cations because they're positively charged. The T kind of looks like a plus sign. Okay? So positive ions are called cations, and metals lose their electrons to form cations. Now, the fact that they have these loose valence electrons, that's what causes them to be good conductors of heat, good conductors of electricity. Those loose electrons can sort of move around. The fancy name for it is delocalized. So we have a chunk of iron or a chunk of copper. The individual electrons around those atoms, they don't always just stay with their own atom. They kind of move around. And that's what causes metals to be good conductors, causes them to be malleable, meaning when we hit them with a hammer, they either flatten or bend. They're ductile, meaning that we can shape them into a wire shape, and we can conduct electricity through them. They're shiny. And metals tend to be solids at room temperature. And we say that the metalloids are on the left side of the periodic table. So here's what we mean by the left side. So here's my periodic table. And if you look at our periodic table up on the wall here, you'll notice there's one little difference. And that's that there's a dark black line. Okay, so the dark black line is right along here. Okay, and we kind of think of that as our dividing line in our periodic table. Okay, so when we say that metals are on the left side of the periodic table, what we're saying is all of these, with the exception of hydrogen, all of that underneath okay, that's the left side of the periodic table. Those are the metals. Okay, there's only one metal that's a liquid at room temperature, and that's mercury. And on our periodic table on the wall, it's in blue. Okay. So those are our metals. So now we're going to talk about the nonmetals. Okay. Nonmetals are just what you would expect them to be. They're the opposite of metals. All right. So notice that metals have only a few valence electrons. Nonmetals have a lot of valence electrons, okay, 4 to 8. Nonmetals don't like to give away their electrons. They like to sort of hoard them, so they gain or share their valence electrons. And because of that, when nonmetals form a charged particle, form an ion, they become negatively charged. and they're called anions. Everything else is just the opposite of metals, right? Metals are good conductors. Non-metals are poor conductors. Metals are malleable. Non-metals are brittle. That's the opposite. Brittle means that they break. Metals are ductile. Non-metals are non-ductile. Metals are shiny, or sometimes the fancy word is lustrous. Non-metals are dull. Metals are always solids with the exception of mercury. And non-metals can be solids, liquids, or gases. They can be any state at room temperature. And they are on the right side of the periodic table. So when I say the right side of the periodic table, here's what we mean. Okay, so here's my periodic table again. And we've got our dividing line. So my nonmetals are these elements and these elements, and then hydrogen. Those are my nonmetals. And we can tell if a substance is a nonmetal by looking at its properties. And we can say that if it's one of these elements in this corner of the periodic table, it's going to have the properties of a nonmetal. Okay? So there's always an exception to the rule, right? And so the last group we're going to talk about are the metalloids. And the metalloids are the ones that touch this black line, so with the exception of aluminum. So these are my metalloids. So that's where they are on the periodic table. Everybody except aluminum that is touching that line, those are the metalloids. And it's not a coincidence that they're kind of on the borderline between metals and nonmetals. Okay? So what you would probably suspect because of where they are, it's probably because they have some properties of metals and some of nonmetals, and that's exactly right. So here's my metalloids. And they're really very, very unique elements. Each one has a different set of properties, but the properties that they have don't necessarily match up all with metals or all with nonmetals. So an example is silicon, not to be confused with silicone, that's something different. Silicon, it is shiny, and it's a conductor. Which would make it seem like it must be a metal, right? But it's also very brittle, meaning that if we hit it with a hammer, it breaks into pieces. So it has a mixture of properties. every one of the metalloids has a different mixture of metal and non-metal properties. They used to be called semi-metals because they've got this weird mixture. Silicon is just one example. So, physical and chemical properties can be used to identify substances and to also classify them into groups. Any questions about those? Okay. So this is your assignment for today. You'll notice in here that we've got different statements, like a diamond is harder than titanium. And then we want to classify this as one of the four, either a physical property, a chemical property, a physical change, or a chemical change. So the fact that a diamond is harder than titanium, that would be a physical property. And so we're going to put an X or a check mark in this box. Only one box for each line, okay? So go through and classify those.